We're gonna start today with something I've shown you already, but we're gonna do it a bit cleaner this time in an actual editor, but just something disconnected. Microphone still on. This is still connected. What's going on? Okay, no taken. Don't touch cables. I touched the cable, didn't I? Ooh, okay. We'll see how that worked out later. Microphone is still recording. The screen is still there. Good. Good start for the day. Alright. Let's create a class. And since we're not about these, I'm gonna include the accessors here. I'm gonna do public everything. Public class player. And the player... Well, we keep it empty for now. And we're gonna have public class monster. And monster will have it's a public int health. Let's do it right like this, and public int strength. Oh, that's sounds good. And public monster. Create a constructor, which is gonna receive health and strength. And this is gonna be equals health and strength equals strength. And then we're gonna have an option for player, which is gonna have public and what's gonna have health and public player. Well, we say the player always starts with 100. Let's make it easy. And then we're gonna add a method for public void get attacked by a monster. Like that, which will then health equals, oh, let's make it easy, minus equals monster dot strength. Right, simple enough. And in return, monster dot health will, let's say it will take damage as well. Oh. Yeah, not bad. So I'm gonna have a player equals new player that, and we're gonna have monster, which is monster with, let's say, 10 health and 4 strength. You can do player dot get attacked by the monster. And if we play this out now, if we were to play this out, the player would lose 4 health. And the monster itself, during the attack, would get hurt as well. And would get hit by 2 damage. So it will lose 2 health. Should be pretty straightforward. Nothing you haven't seen a couple of times already. Let's say we have a second monster. Let's say this is monster 1 and this is monster 2. The second monster will be the same as the first one. And maybe we're gonna add a third one. 3. This one will be a bit tankier, but also a bit weaker. And then let's do the opposite. Last one is gonna have double the health, but only quarter, double the attack, strength, but only quarter of the health. The previous one, or half of that one. And this is monster 4. When I want to attack the player with these monsters, I'm gonna have to do it monster 1 and monster 2, 3, and 4. Which is a bit tedious, especially once we start having more monsters. Okay, let's say we have a couple of 100 monsters, potentially. I would have to write them out all one by one, which is lots of variables that I have to manage, which is, yeah, something I'm too lazy for. And even if we accept all the extra work that I have to put in as the programmer of just writing this out, maybe I want to add a specific mechanic where the player isn't getting attacked by a single monster at a time, but by multiple monsters at the same time, and that changes things. So maybe I have to add something like this. Monster, let's call it monster A, and this monster B. And we're still gonna decrease the health by monster A.strength plus monster. What's going on? I think I switched my keyboard layout. Okay, that's better. Monster B.strength. So, but the health will not get reduced anymore. If I attack with multiple monsters, they can distract the player so he can't fight back, and they're much more dangerous this way. So, as a player, you're encouraged to single out monsters and fight one-on-one, because if they group up, you have a harder time fighting them all off. You should maybe even get a bonus here, +2, let's say that. They do more damage in a group, and they don't take health damage themselves. This is for 2 monsters. If I want to have that for 3 monsters, I would have to make another method get attacked. So I'd have to make a new method get attacked for every combination of monsters that want to attack the player. Actually, why did I write this out as separate? Doesn't matter. So I have extra work to create all these monsters, I have extra work to attack with these monsters, and I have extra work to make sure that I have different methods for attacking the player depending on how many monsters attack. All that extra work makes it really hard for me to justify adding this mechanic and adding all these monsters. So we have to find a better way, because I do want that mechanic in there. Whoop, I want to scroll down like that. So what we do is we take advantage of a clever little trick that I definitely didn't come up with myself. Just to make that clear. Group, actually let's call it group of monsters. This is something we've done before. I think 3 episodes ago I demonstrated this very briefly at the end. We have a new class group of monsters, which... okay. Which internally will store public monster, which will store a monster. So an instance of this class here. But it will also public group of monsters next group. store an instance of itself. We keep in mind that these are classes, so reference types, meaning they are stored on the heap, not on the stack. All of these variables up here are simply the addresses where we can find the specific monster on the heap. So this variable simply stores the address on the heap where we can find a specific monster, and the address on the heap where we can find another group of monsters. This is not a struct. I can store a field with the same type as the type I'm defining it in, as long as it's a reference type. Can't do this with a struct. We talked about that. Can't store an infinitely large amount of data, but I can store a reference because the reference can just be null as well. Don't need to have an infinitely long list of groups of monsters that reference another monster. I can have null, so it references nothing, and I can also, just referencing myself, create a circle somewhere. I'm just gonna minimize this a bit, so we have more space. It's still there. Another advantage of modern editors and IDEs, I've used that before, I didn't really explain it, but we have brackets that go from here to here, the entire class, and the system understands that this is one block of code, so I can just shrink it down into a single line. I can still see that there's a block of code in here, I just don't see the code, and if I am interested in reading it, I unfold right now and read it. Saves a lot of space. Right now we're not interested in the details for these two classes. We're interested in their existence, but nothing more. We're gonna keep the player, that's fine, but instead of creating a new monster, a new variable, we're gonna create one group of monsters with a lowercase o. Let's call it just group. It's gonna be a new group of monsters. And again, lowercase o. That's better. This is using the default constructor, so it's not doing anything. We're just creating a space on the heap that can store one group of monsters, that can store one reference to a monster and one reference to another group of monsters. We take up the space on the heap for these two variables, these two fields more specifically. And all the memory is starting at zeros. Again, we've talked about this. So this and this will both start at null. Look. Group.monster is currently null. So we can just fill it, not lose anything, with a new monster. We can do this, no problem. We create a new monster. We reserve space on the heap for a monster. We call the constructor for monster with 10 and 4. So we fill the data that was previously just zeros with 10 and 4. And the address for this new monster on the heap is stored in this field of monster. And then we can do group. Let's maybe put this a line further down. Group of monsters. Again with the lowercase o. I'm having a hard time getting off the shift key every time. It's a problem I have not just during the streams. Every time I type something, I tend to keep the shift key up for just a bit too long. So I'm typing 2 uppercase letters in one go. It's weird. Anyway, this too will get a new value. We call the constructor, and we're gonna create a new group of monsters. See, that's what I mean. Again, just a little bit too slow. Anyway, group of monsters will be new group of monsters. So we can go group of monsters. If I take my time, it works better. And this... Oh wait, not group of monsters. We call it next group. My bad. Next group, it's better. Next group is new group of monsters, and next group dot monster would be 0. But we can initialize it with another 10.4. And we can do group dot next group dot next group. Initialize this to a new group of monsters. And there I go again. Monsters, nope. And I can keep this up for any number of monsters I want. Which isn't exactly better than the old system, because I still have to write it out one by one. And actually I have to write 2 lines now for each monster instead of just 1. But with this system, we can change things a bit. Let's remove this and this as well. We start off with one group of monsters, freshly created. And then we group of monsters. Ooh, newest group, let's put it like that, with group. We have now 2 different variables that both store the same address on the heap for the same object on the heap, the same group of monsters. But we store it as 2 separate variables, so this will have the address and this will have the address. And if one of them is used to change this group of monsters, it will change the same value on the heap. But if we change the variable newest group, it's not going to change group. Keep that in mind. This is in direction. Both of these are separate variables that just happen to share the same value right now, that point to the same address on the heap. Let's create a for loop and I equals 0. Again, you've seen this before, so you should know where I'm going here. I'm taking newest group dot monster equals new monster. So the same code from before. And I'm gonna go for 10 and 4 again. And newest group dot next group will be a new group of monsters. So just like before. But now we're gonna do newest group is equal to newest group dot next group. So we start off with this first group of monsters, the first object that we have on the heap, and we just put the address, copy that into newest group. And now for this one address on the heap, we're adding for the first field monsters, the address to a newly created monster. And for the field next group, we add the address of a newly created group of monsters. So this first group we created is now fully filled up with actual values for monster and next group. And then in this line, we start off with the right side. We resolve this variable reference. We see newest group. We point to an address on the heap. Dot operator. We read a value from that address. We read the value from next group, which is this newly created group of monsters, the second newer group of monsters. And we take the address that is stored in here and put that into the variable newest group. We only changed newest group. We didn't change the value on the heap, we only change this variable news group that is on the stack in our main method that is pointing to a part of the heap. The heap itself isn't changed by this, we only changed this variable. Group still points to the original first group of monsters. And we do this 4 times. We do it for I equals 0, 1, 2, and 3. And for the 5th iteration, I would be equal to 4, which is not less than 4, so we drop out. Once we're done here, we will have one group of monsters, which has one monster with 10-4, and points to another second group of monsters, which will also store internally a monster with 10-4, and point to a third group of monsters, which will store a monster with 10-4, that points to a fourth group of monsters, which has a monster with 10-4, which will then point to a fifth group of monsters, which will have a null. So maybe to clean things up a bit, we could go actually no, let's not worry about that for now. Point is, in the end we have that bothers me. Let's do this for just I equals 3 and do this on its own in the end. Yeah, that's better. So the fourth group of monsters will now have a monster, but the next group will be null and not point to another group. That's cleaner. So instead of one monster, we store in one variable, and then a second monster and a second variable, and a third monster and a third variable. We now have this group and a couple of extra lines that can create as many monsters as we want. 300 monsters, all created with 10-4, 10 health, 4 strength, but 300 monsters in total. And they're all still accessible. I didn't have to write them out one by one. I didn't have to call the constructor with a new line each. And I can just adjust the number I need on the fly. This doesn't even need to be a constant. Right now I'm hard-coded, it's hard-coded to 3, but I can make this value dependent on some calculations or maybe some user input. And to get all of that data, we'll just go group of group of monsters, some group, and we're gonna do the same with it up here with newest group. We just do kind of the reverse. Start with group like that. Let's also remove this. Actually, let's do that not in here. Let's adjust class player, because that's where we get the second advantage. We don't have to write out each creation, and we don't have to write our code for a specific number of monsters. And down here, we don't have to read out the monsters one by one. We can make the getAttack method, change this to group of monsters. Monster group, and since we already have a variable, we don't need to store a new one. Whoop. Okay, that's better. We can use another for loop to simplify things a bit. For group of monsters, I did it again. Group of monsters, current group, well actually let's do I, just for the sake of it, equals monster group. Then the condition, we do this as long as I dot next group. No, as long as I is not null. Yeah, that's better. And to advance in the loop, we're just gonna say I is equal to I dot next group. There we go. This code will now go through this weird construct we've created that stores any number of monsters. We can call this method for a single monster, for 3 monsters, for 4 monsters, for 300 monsters. Doesn't matter. Any number of monsters we can use this one method for, and it will deal with it. And for this thing we can now... Let's see, we have... Let's do int count. Started at 0. And for each monster we find, we increase this count. And we're gonna do the... What? Decrement means equals strength. So for each monster we've stored in our group, we subtract the health by the strength of each monster individually. And in the end we can do health minus equals count. So for each monster in the group, we'll subtract the health by 1 bonus value. Actually, no. Let's do it like this. If count equals 1. Let's make this the same we had earlier. If it's only one single monster, then we know monster group itself is the only monster. We can just do monster group dot monster. Should have done this as well in here. My bad. That's better. Monster group dot monster dot health. Yeah, like that. So group dot monster dot strength divided by 2. So if it's a single monster, we decrease the health of that single monster by its own attack value. Else, if there are else if count equals 0. If there are no monsters, we're gonna return, do nothing else. And else if there are any monsters, plural, we're gonna decrement the health by that count, just as a group bonus. The more monsters we have, the more the additional damage, and no monster gets its health reduced. And we do it this way, this return doesn't do anything else anymore, so we can also change this to greater than 1. Alright, slightly convoluted, but this should do the trick. Let's see, is equal, not equal, yeah, that covers it, just about it. Can do player dot get attacked by group, like that. Just by changing this one value, we can change the number of monsters we have, and the attack method will take care of all the logic no matter how many monsters we have. And it's just this one piece of code we write. It's more complicated than if it's just a single monster, but we get a lot of flexibility with this. Variety suffers a bit, so we could, for example, do it like this. We copy that out. We do 3 like that. Maybe then we do 2 tanky ones. 22, and then maybe, yeah, just let's keep for the last one the big attacker. So we can still cause some variety within the group. It doesn't need to be always the same monster. We could also create an if in here, if I less than 1, and then do different values in the monster constructor based on the value of I. Different variations or the same code. This method allows us to store as many monsters as we want without creating variables for every single one of them. But it does have its downsides. The first downside is the code is a bit complicated. I mean, if you're used to it, it's quite simple, but you can still make mistakes. Just, I have to always keep in mind I have this structure of taking the first reference and taking the next reference to get to the next heap object, and then go to that reference, and they all have this very specific order. I have to keep track of all of that and write all this code out to step through all the different monsters in the group. We can try to write methods for that in group of monsters. We could write static methods in here that would include code like this to make our life a bit easier. So you don't have to repeat the same code everywhere, but it's still a bit complicated. And especially if you include special code for the creation of monsters, you probably want to do all of this yourself. Just to get the ratios and the calculations for what values a monster gets right. Another issue is with this system, I have a group of monsters. And it's this one complete group of monsters. I can't easily single out a single monster. I can, for example, when I'm going through the different monsters, I can check if count equals 5. Well, then I know that in this one instance, I is the 5th monster in my group. And I can do something specific with the monster number 5. But I still have to step through the entire group to find that monster. I have to step through the group and count along to know where I can find a specific monster. So usually it's a case of I'm treating this as a complete group and the monsters are kind of losing their individuality. Maybe I want to single out a specific monster and do something with that. Who knows? But the largest, why is it? Please don't scroll down all the time. Let's maybe do it this way. The largest downside is the inefficiency. Each group of monsters is storing one monster and one group of monsters. Or better, it's storing the reference to one monster and the reference to one group of monsters. These references are just addresses in your memory, but they do take up some space. You need to store that address somehow. Even if it's just a single number, it is still taking up space. If I have a couple of hundred or thousands or millions or whatnot of monsters, this will waste a lot of space just to point to the next group of monsters. If we have 300 different monsters, well, then we have to store 300 monsters on the heap. Can't avoid that. Okay, acceptable. But besides the 300 monsters, we also store 300 groups of monsters. Keep in mind, each monster exists in the context of one group of monsters. So that's one additional address we store for each monster. And one additional group of monsters reference. So 300 monsters, actual items on the heap, plus whatever space we need for a reference to a monster 300 times, and whatever reference we need for a group of monsters 300 times. The space we need, if you're not sure, it's probably going to be 64-bit. Sometimes it's only 32 bits. These addresses depend on the maximum size your program can allocate. Again, if you're not sure about that, you're probably using a 64-bit program. That's kind of the default, unless you specify you want x86, well, 32-bit, then it's a 32-bit. And maybe you have some weird, I shouldn't say weird, some edge cases where you have some special hardware, special configurations where you have different values, but either 32-bit, so equivalent to an integer. More likely you have a 64-bit address space, which means each of these is as long as a long. So you spend 128 bits just to store 300 monsters. That's overhead. Let's maybe have a quick look at, I'm hoping this will work. At the heap. Oh, that worked right away. Unexpected, but not complaining. So we had the stack. Let's make this nice and small. We had somewhere a monster group of monsters. Yeah, whatever. We have a group of monsters, and we have the heap somewhere. And on the heap we have a group of monsters. Just make GM, which will have one monster and another group of monsters. This might be at address 54321. So that's one group of monsters. Somewhere we have a monster. This might be address 333. And it will internally store two integer values. And this might point to there, 333. And we have another group of monsters. Say 6, 7, 8, 9 of monsters, which will have another monster, another group of monsters. Uh, 6, 7, 8, 9. This first group of monsters will maybe point in there. And this can now have another monster. Address 100. It's another monster. Int. And this might be just 0 and it's not pointing anywhere. Not a bit chaotic, but this is essentially the structure we have. We have individual monsters on the heap somewhere, and we have these other objects that are a group of monsters that point to a monster on the heap somewhere, or to another group of monsters that puts them into the same group. And all we need is just the address for the very first group of monsters, and we can find everything else from there. Let's try to organize this a bit. Let's try to think about how we would be able to solve this issue just a bit more efficiently. Imagine you have some important documents, like important contract. Maybe you got a letter from the tax office with some important instructions on how not to pay extra, avoid any late fees. And you want to read through that carefully. You want to store that safely away somewhere so you can reread it. And you need to be able to read that in a proper sequence. So naturally, you would just take each page of that contract, that large sequence of documents, and just tape it somewhere on the walls, or maybe put it next to the toilet. Maybe you plaster one below your desk, and another one is put into, I don't know, the window on the outside, so everyone else can read it too. That makes sense. Just spread it everywhere where we can. Our entire whole house is now filled with individual pages of this one large important document. Well, obviously not doing that, hopefully. You take all those pages, put them in one sequence into one binder. So they're nice and organized and compact, all in one go. You just take out this one binder that you put away somewhere in the cabinet, and when you need it, you just put out that one binder and you open it, and you have all the different documents you can just cycle through in their correct order. You pick out whatever page you need. So instead of spreading all our objects around on the heap, we could just do one monster and then put it on next monster and then another monster. Put them all right next to another in one orderly fashion. Could be address 1000, this could be 1001, this could be 1002, 1003. These all have individual addresses on the heap, of course, but they're all right next to one another. One large sequence of bits in memory that represent 4 different monsters. They're not spread out everywhere, they're very organized. If we do this, then we only have to remember where we put this large thing. We don't have to remember where we put each individual monster, we just remember where we put the sequence of monsters. Could, for example, just remember, hey, where is the whole sequence starting? What is the first address where our sequence of monsters starts? Address 1000. So we just remember that's the very first monster. And if we want to see the other monsters, we just go, alright, what's the next monster if we assume there's another one? We know how big a monster is, how much space it's gonna need. Monster in our case stores 2 integer values. So we go further by 2 integer values, and then that's the next monster, which will have 2 integer values for the second monster. And then once those are done, the next integer value that we can find is for the third monster, and so is the one after that. And after those integer values, we get the fourth monster with another 2 integer values. we know how large each monster is. So if we go in memory, we just have to figure out this is where we all start. We'll take the length the monster will have, add that to this first address, and this is where the second monster starts. And then if you go forward by exactly the length of one monster, that's where the third one starts. And the fourth one. We don't need to store each address, we just calculate based on the very first one in the sequence. Very, very convenient way to store the data. No overhead with all these different objects that have to keep reference to all of these individual monsters that might be plastered everywhere. And as a neat side effect, it makes our memory a lot more organized, which is helpful for the garbage collection. Instead of reserving new space for every single monster and calling a new constructor every time to reserve that space and whatnot, no, we're just reserving space for 4 monsters all in one go. So we only reserve space once, and we have it all ready. Much faster, much more organized. And we can use this feature in C# using a special syntax. Let's forget about group of monsters. Let's go back up here and think about what we did. We stored a single monster that's followed by another monster, that's followed by another monster, that's followed by another monster. Store a single monster, followed by another one, by another one, by another one. We definitely create a monster. We just create enough space for 4 monsters. So the syntax looks almost as if we just create a monster singular. Like this would be me creating a single monster. We just have to change this now to not store a single monster, but reserve space for, let's say, 4 monsters. And the syntax is gonna use the third type of bracket that C# uses. And we're gonna start in the front, because we have to tell the compiler that we're not interested in storing one single monster, we're storing a sequence of monsters. This is not supposed to be the address of just one monster on the heap. This is the very first address of a sequence of monsters. That's a very big distinction. And we have to tell the compiler that by adding some brackets after monster here. Open square bracket and closing square bracket. Like a little box we draw here. And this will tell the compiler that we're not creating one monster, but a sequence of monsters. We reserve space on the heap that can store several consecutive monsters. That's all we need to do in the front here. The constructor will also need to change. We still use the new keyword, we reserve space on the heap. Definitely, quite a lot of space actually. And we still reserve space for monsters. That's what we set in front here. Reserve new space on the heap for the sequence of monsters. The compiler knows how much space a single monster will take, so new monster itself would not be a problem, but we need to tell it now how many monsters will be in that sequence. We have to tell it beforehand how much space will it need. And to do so, we don't add the normal brackets and call the constructor. We use the square brackets again and give it a number. 4. We tell the compiler, create a variable that stores the address to a sequence of monsters. A sequence of monsters. And this address will point to this new space on the heap that we reserve for exactly 4 monsters. It's important, this is not a constructor. This is so far just an extension of this new keyword. We didn't call the constructor for monster yet. We in fact haven't created any monsters so far. We just reserved the space necessary to store 4 monsters. More specifically, what we stored wasn't the 4 monsters. What we actually stored was 4 addresses for a monster. This is where we get some important differences between classes and structs again. Monster is a class, a reference type. So whenever we store a monster, or a variable for monster, we only store the address to point somewhere on the heap. When we create a sequence of something, we don't store that one single thing, we store a sequence of that thing. That thing being the address to somewhere on the heap. So I lied to you actually. Right now, this sequence of monsters is not what we created. What we actually created was a much smaller sequence of addresses that point to monsters, which could actually be everywhere on the heap. Completely unorganized. We cheated a bit. We created this sequence of just the addresses. This is the continuous sequence. This is on the heap, no problem. The sequence of individual values on the heap, but the actual monsters we store are still all over the place. If we want the original idea of storing everything nicely and organized, let me see if I can get back a few times. That's better. If we want to get back to this, we have to change our monster from class to struct. If we do this, then a monster is not a reference to somewhere on the heap, but just a value in of itself. And a sequence of monsters is a sequence of this value in of itself. So a sequence of 2 integers which represent health and strength of a monster. Doing this will mean we create a nice little sequence of monsters very strictly organized on the heap. That's the important thing here. Struct means monster itself is a value, but despite us creating monster as a struct, as a value type, the sequence of monsters is not on the stack. A sequence is inherently a reference type. Sequences are only created on the heap. And it's not actually sequence, it has a name, it's called array. What we have here on the heap is an array. This is an array of a value type. So each single element in this array is a full valid value. It's an actual monster with both integers right now, because monsters are now structs, are now value types. Each of these elements in the sequence is a full value. 2 integers, everywhere. If I change struct back to class, and monster is now a reference type, then we store a sequence of addresses still on the heap. It's a sequence, it's an array, put that on the heap, and they point to monsters everywhere on the heap. The actual monsters could be anywhere. No organization there. Just like before. If you want it neatly arranged, you put that into a struct, a value type. Like that. But let's go for now back to class, the way we did it before. That means we create an array, a sequence of addresses. This sequence of addresses is stored on the heap, and these addresses all start, as all newly created objects on the heap start, with everything set to 0. We have 4 entries on the heap now. Each entry has space enough for one address that can point to a monster. But just like the normal new keyword that we use for constructors, it will start off the memory set to zeros. So all these addresses to all these monsters, these 4 monsters we reference, are null. We still have to create new monsters and store the references, just like we did with a group of monsters. But the syntax looks a bit different now, because arrays, as you can see, have special syntax, have special rules how we use that. Let's still try to use a for loop, just like earlier, and I equals 0, I less than, let's do 4 now, and I. So, we still create 4 monsters, still with a for loop, just to keep track of how many we've done so far. We can still use a normal constructor to create the monsters. Monster 10, 4, right? But the way we store it is different now. We start off by referencing monster. Monster is the address for the array on the heap. So monster itself is an address that points to a sequence of addresses on the heap, where each address within that sequence can point to somewhere else on the heap again, but then to a monster specifically. So an address that contains addresses that point to monsters. I now want to change one of these 4 addresses we can store in monster to point to this specific newly created monster. With a group of monsters, I would do monster.monster. But with our new syntax, I don't address just one entry of this list of group of monsters. Monster is targeting this entire sequence in one go. I have to somehow tell the system now which of these 4 monsters I want to change. I have accessed all 4 of them already. Not just the first one. I can see all of them in one single variable. To target one specifically, I use again the square brackets. They are heavily used for arrays, for a lot of things. And up here, I left them empty just to mark this as it's a sequence of monsters, or monster addresses specifically, not just a single one. And here I used them to tell the compiler it's supposed to be a sequence that contains 4 elements. Now I want to use these to tell the compiler which of these 4 addresses I'm going to change. And I can do that by just giving it a number. I can give it 1, 2, 3. And Each number represents a different address. What I said earlier, we start up here. It's a bit laggy, I think. There we go. We have the first address in the sequence. Well, more specifically would be in here actually. But we have the very first address, that is what monster points to. And we know how long each element in the sequence is. So by simply telling it we want the second monster or the third monster, we multiply 3, for example, by the length of each element, and that gets us the distance down here. Which will actually, or if we put that down here, the length of each element times 3, 1, 2, 3, will get us down here if we start up here. That plus 3 times length will get us down here. That will get us actually the fourth entry. So multiplying by 3 will get us to the fourth entry. Multiplying by 2 will get us here to the third entry, to the start of the third one. Multiplying by 1, just getting one length, will get us to the entry, the starting point for the second entry. Multiplying by 0, so just taking the address itself, that's where we find the first entry. This goes back way earlier to the very first lessons. We always start counting at 0. Memory address 0 is the very first address. And here you can see one example where this is also true. It's for arrays. The very first entry is the 0th element, so to speak. In our code, if I put in 1, it means take the size of a monster, or in case of a monster that would be the length of an address for a monster, multiply it by this number and add that to the very first address where our sequence starts, which is the starting address of the second monster. So we put on a 1, but that will give us the second monster. If I add a 2, that will point to the third monster. A 3 will go to the fourth one. It's always one more. Adding a 0, that would get us to the very first monster. Just take the address to the very first monster and don't add anything to that address. Leave it as is. Use the address as it is. It's one of the possible causes for one-off errors, or off by 1 errors. It's one of the most confusing things if you just start with arrays. 0 is the first. We count starting from 0. 3 would be the last one. 3 is the fourth monster, and we only have 4. So the total length of monsters, this array of monsters, is 4. That means the last monster is at 3. Keep that in mind. Of course, I don't have to put on a solid number in here. I can use a variable for that. And quite conveniently, I have a variable in here that changes from 0 to including 3, with each iteration. So doing it like this will get me a for loop that will create a new monster 4 times, and each of them will be put in a different position in this array monster. And the nice part is I don't have to observe any order. I could assign these values in any order I want. Right now I'm starting at 0, then 1, 2, 3, going in sequence, but I could set the value first for monster 2, then for monster 3, then for monster 0, then for monster 1. Completely up to me. There is no inherent order in here that I have to observe. I can access every monster in that sequence whenever I want, without going through the other monsters first, making this a lot faster. I can do that in player as well. When I call get attacked, I can now just pass on monster, or let's actually call it monsters, plural. Because it's not just one monster, it's a group of monsters, of 4 monsters. Get attacked will receive this array of monsters. That means I have to change the type in here as well. Not to monster, but to a sequence of monsters. An array of monsters. That means I have to now iterate through this entire monster group. And in of itself, not big of a deal. Monster group is a variable that exists just like monsters up here. I can use the square brackets to access specific monsters that I'm interested in. No problem. The only issue is right now, I don't know how many monsters there are. If I were to try and go for monster 100, which would be the 101st monster, this won't work. We only have 4 monsters in the sequence. 100 is not possible. That's outside the bounds of our array. We have an upper bound of 4 monsters. How do we know that down here? I could pass on a variable, like just use count, but just pass it on, and that way I know I can only go up to count. That's the number of monsters I have. I don't need to though. Monsters is a sequence of something, so it is bound to the heap already. But what we have in here, or here, is not just the actual values in a sequence. We have on top of that something more. There's something more on top where we start the actual object. If you have an array, this array will carry with it some additional information, most importantly, the number of elements in the sequence. Monsters will keep this number 4 stored in itself. Monsters itself will store this number 4 and we can reference that. So monster group down here in the player already has the number 4 stored in itself. We just have to access it. You can think of these arrays as their own type. No, this is not the actual type. This is just to demonstrate something. But public class array, public read only int length. We can pretend that this is actually an array monster group, and that means I can monster group dot length. I can access this integer field. Only the actual type works differently. This is special syntax after all. But if you can just imagine that this is a field in a special class that we're receiving. We have created a special class that's not a monster, but a sequence of monsters. And it has one integer field called length. Actually, it has two length. There's length, which is an integer field, but still can't get used to the key combos. The sequences can go very, very, very large, so a single integer might not be big enough to store the number of elements. There's even a long length, which is a long. So int l is long length, and we have long length, which is long. You're not going to work with these very often, probably, but there might be some edge cases where it's becoming useful. It's rare to see it though. Usually you have just length, and that's way more than enough. So let's use it up here as well. If I want to, for example, change this to a sequence of 40 monsters, I would have to change that twice. But we can change this up here as well to use the field that's stored in monsters, and that way automatically adjust the iterations of this for loop to however many items we have. 4 or 40 or 400, doesn't matter. Just change it once in here, and this for loop will go through each individual monster in that sequence. By the way, sequences can have a single element, that's perfectly valid, and you can have 0 elements. And these do sometimes make sense. As weird as that sounds, a sequence that doesn't store anything is still useful, just as an address that's not pointing anywhere is useful. So null can be useful, though it's often a burden. It can be very useful. An array, a sequence of something that doesn't have anything, can still be useful. And that would be reflected. Length would be just 0. It's still a valid sequence. Let's go back to 4. Just as we did up there, let's copy that code. I'm using actually a lot again. Monster group. Copy the code over, and we now iterate through the entire group of monsters, which is an array of monsters, and subtract the health. And instead of count, we can go monster group dot length down here. It's exactly one monster. We remove the health of that one monster. Because we know it's one monster exactly, we can rely on this 0 being correct. We have exactly one monster, so there is something at position 0. And if it's monster group length greater than 1, we have more than one monster, then we do additional damage based on the number of monsters in that group. And we've changed our code. All I gotta do is change this number up here, and I get a different number of monsters. And similar to before, I can just make a second loop if I want to have different monsters. Yeah. Okay, let's go this way. Second set of monsters. The second one will then get 20 and 2, for example. Now I have to, however, adjust this a bit. To start at 2 and then go to 4. If I don't do this, then I would just rewrite position 0 and 1 again with a new monster. Monster 0 and 1 are overwritten here and then here again. Positions 2 and 3 never receive an address, and they would actually be null still. and the very first monsters we created, they're lost forever. Garbage collection will take care of them. In that case, it might make sense to split this up. We can do int I. We just declare the variable here, so we can reuse it. We don't do anything in here. And, for example, do it like that. Or we do it like this with an if I less than 2, and that, else 22. Let's clean this up a bit. Don't like this. Oh well. That's how we can use an array. There are some special things you can do with arrays. There are some special types of arrays, and there's even an entirely special syntax around a very special type of array that we're not going to talk about today. Since time is running out, we're gonna quickly mention one last thing, which is very, very, very important for you to understand, because it has far-reaching consequences. When I use let's go back here. When I create this array of monsters up here, I'm using the new keyword to reserve space on the heap. And I reserve that space for a sequence of 4 monsters. So we reserve exactly this space. Not more, not less. And if it was a struct, we would reserve this space. Exactly. If I later decide I want to have a 5th monster, I have an issue. There's space for 4 monsters in here. This space down here was not reserved beforehand. It might be that the space is free and we could actually use it for a 5th monster and make that work, but it could also be already occupied by something entirely different. We don't know. There are no guarantees for anything. Arrays are fixed size, meaning when you create an array, you have all the freedom to make it as big or small as you want. But the moment it was created, the moment this space is reserved, it will be fixed, it will stay at that size forever. You can't make it smaller if you decide I don't need that much space anymore. And you can't make it bigger if you decide I need additional elements in there. It will always, forever, stay at this exact size. If I didn't need 4 monsters, I could still reserve space for 4 monsters and just fill the first 3, and no big problem. You might have issues down here because... oh right, I didn't change this code. Why did no one complain? Monster group... that's better. Monster group I.strength. If I only fill the first 3 monsters in this array, well then once we hit monster number 4, monster 3, it will be null, and then we try to reference with the dot operator address null, which is an error. Runtime doesn't like that. There is nothing to reference, so this dot operator will not work. We get an exception, runtime error, and your program might crash. So we would need to add additional checks in here to make sure that the monsters we try to reference actually exist. But aside from that, the code will work. If I try to make more monsters, that'd be an issue. I can reserve the space and not utilize it, but I can't utilize space that I never reserved. So what do we do if we absolutely need additional monsters? Let's say we have some part of the code that creates this array of monsters for us, maybe the class monster itself, but then we later decide we want to merge two existing groups. Like the player has aggroed a few monsters from one zone and then is slowly luring them over to another zone, and the monsters in there decide, let's team up and teach the player a lesson. So you need a new group of monsters that combines two other groups. You can't just squish them together. These are two distinct spaces on the heap with a fixed amount of monsters. The only option you have is create a third new sequence of monsters that combines all the monsters from the first group and the second group. So let's say we have the monster group A, let's just call it A, is sequence of 3 monsters, and group B is 10 monsters. Well, that's not good a number. Let's go 5. Something disconnected again? Hooray! Microphone is still picking up? It is. It's a USB microphone, so I'm a bit paranoid. So to merge these two, all we can do is create a new array, monster merged, which is a new sequence that has enough space for both groups. So I would have to do a.length plus b.length. I know how big the groups are, so I can reserve the space for this new group based on that length. I don't have to hardcode this value. I don't have to know beforehand, before running the program, how many monsters I'm gonna need at runtime. It's just the moment you do know and call the constructor for this sequence, not the constructor for the monsters, I need to have some value available for the runtime. It can still be dynamic. It's just a read-only value. Once you set it, it's set forever. And now we have to copy over the values by hand. We have 2 sequences, so we're gonna do first one int I equals 0, I less than. We make this dynamic because we are not sure how big the group is, maybe. Length, and then plus plus I, and for, let's do it like this. What's going on? Okay, seriously, what is? Oh well. And then we can do merged equals a.i, or a, not dot I, ai. I don't like that. I do I as well in here. So position 0 in the new merged one will be equal to whatever is in position 0 in A. Position 1 in the new merged sequence, the merged array, will be equal to position 1 in A. And so forth. And then we do the same. I never learn. Then we do the same with B. Except with B we have a little issue now. We're writing the first value from B into the first value for merged, which is already filled with the first value for A. That's not how we arrange these 2 sequences. We actually have to keep track of the progress and merged with a separate variable. I was going to use J, that's the classic. We have one I, so we go with J for the next one. J And we could do something like this, j++. Looks a bit convoluted, but it's perfectly fine. We could also do this. If you remember in the for loop, the meaning of commas and semicolon are a bit weird. Semicolon are not marking the end of an instruction directly. They separate the three different parts of the for loop. And commas now take on the role of a semicolon. So we have two instructions in here for the last segment, which will increment I and j equally. But usually I avoid this because it looks a bit weird and just put that in there. Looks a bit cleaner and it's a bit easier to understand what I'm trying to do here. So this is just a very, very standard for loop and you don't get any weird mixed signals. And we do the same down here. Because j is defined outside of the scope in here, starts at 0 and is incremented for each element we add. So after we're done, j will be equal to 3. A has 3 elements, so this loop runs 3 times, so we increment j 3 times by 1, meaning j is 3 when we start this line for the very first time, and then increment further. And then we can do merged. Things would look similar if we don't merge two groups, just one additional monster in that group. So we start off with just one group A, and we want one additional monster. Well, then we have to create a new array, which has one additional length. And still do this. We can simplify it, we don't need j anymore. Copy all the values from A to merged, and then merged can either do a.length equals new monster. So could do a.length, which we know will be exactly the position in the array after the last copied value. So length of 3 means length is 3, but the last position we copied will be less than that, which will be at 2. We could also do merge.length -1. Also very common to see, if you work with arrays, you will often have a situation where you do length -1. Because of this off by 1. We have 3 elements, that means the last element will be length -1. A.length -1. It's the last first equals 0. So like that. The first monster in the array is at position 0. The last will be at the total length of the array -1, position 2, 3 -1. We can replace this A with monsters as well. Make use of the existing one. And then we can do our glass can, for example. And that's how we can increase the size of an array. And that's of course how we can also decrease the size if we want to. We'd create a new array that's smaller than the first one and then copy only until we hit the last one. So getAttack would only use 3 of the 4 monsters we store. That's arrays. Sequences of either addresses or values in of itself, depending on class or struct, reference or value type, that can make working with large amounts of objects or data in general a lot more efficient, a lot more convenient to use. It just has some restrictions you need to be aware of, like fixed size. Though even around the fixed size, there are workarounds. And the simplest one you've seen here. There are more sophisticated ways to go around this, which we will look at in the future, because there are very fundamental types in C# that deal with that kind of thing. That means we can drop this, simplify our code a bit, and learn something new about C#. Arrays. Hooray. This took a bit longer than I expected. I was hoping to get the other types of array as well. I might have overdone it with the explaining. Should have probably sped up a bit. It's hard to do these streams without getting live feedback. It's easier if you do it in a room with people, because then you can have the live reaction. You can see it in their faces if they understand and you can carry on, or if there are any questions left. Live streaming is really hard for this type of stuff. That's one of the reasons I'm doing this. No better training to get the pacing right than blind testing. All right. Have a lovely Sunday, and see you next time.